Everyone, Professor Hartman here. So as usual, I want to go through a few problems that we'll be doing that are reflective, of the homework problems here for Chapter 3. So this is, we're going to be talking about two-dimensional kinematics here. So hopefully, the 1D kinematics has been something that you've been able to get a handle on reasonably. If not, well, the 2D kinematics, it's basically the same thing, right? You're just applying it to two dimensions. So there's the addition of a little bit of trigonometry and a focus on vectors. And of course, vectors are quantities that both have magnitude and direction, as opposed to scalars, which have only magnitude. As you might imagine, in general, vectors are harder to deal with than scalars. And so a lot of physics, particularly after the development of classical dynamics by Isaac Newton in the mid to late 17th century, which was a vector-based approach, was focused on reproducing Newton's physics using scalars. And probably the most well-known scalar quantity is energy. And we're going to be dealing with energy in a few weeks. And actually solving or resolving a lot of these problems that we're doing using vectors, using energy, which scalar-based approach, and hopefully or probably you'll find those a little easier doing it using energy. But anyway, at this point we're still stuck with vectors, so let's get into it. These are from Chapter 3, and so I want to solve these problems. I have a few of them here. Start with number 9. So we have a picture here. It says there are three vectors, A, B, and C. And they're given in arbitrary units. So these vectors, they could be meters, or if we're talking about force, they could be newtons, but we're just going to leave them as numbers here. And they want the resultant of, they want the sum of the three vectors, right? And we want the result of these in terms of the components, and then the magnitude and the angle with the x-axis. So basically what we want to do here is break these vectors into their components, and what you can see, at least for the vectors A and B, there are both x and y components, right? So if we look at the vector A, right, this is going to form a right triangle. So we could kind of go up. This is a little thicker than I wanted. Let's do this one. We could go up like this, and we could call this AY, right? That's basically A in the y direction. And then this piece here to the right, this would be A in the x direction. Try to draw a straight line as best I can. Call that AX. And we can use SOHCAHTOA, right? What we can basically do here is say, all right, looking at this thing here, well, the sine of 28 degrees, that's going to be the opposite over the hypotenuse. So that's AY over 44, right? So AY over 44. And if we just sort of rearrange this, we'll find that AY is 44 times the sine of 28 degrees. So we can solve for AY. So AY, obviously you would need to put this into the calculator. So the y component of A, right, that's going to be 44 times sine of 28. Make sure you're in degrees and not radians. And that's going to be 20.7, whatever the units are. So that's AY. By the same logic, we can figure out AX. We'll say the cosine, right, of 28 degrees, that's adjacent over hypotenuse. The adjacent is AX, and the hypotenuse, that's still 44. So that's going to be AX over 44. So if we go ahead and solve for AX, that's going to be 44 times the cosine of 28 degrees. And we'll put that in the calculator. So 44 times the cosine of 28, and we get 38.8. So that's AX, 38.8. Okay, and then we'll do the same thing for the B, right? So here, this would be like BY, and then here we would have, and the direction matters, right? And I'll sort of show you how that works here. We'll have BX like this. And so by the same logic, right, BY, right, that's going to be 26.5 times the sine of 56 degrees, right? And so that'll be, let's see, so 26.5 times the sine of 56, and I get about 22 there, 22.0, I guess, is BY. And then BX is going to be the cosine component. So that's going to be 26.5 times the cosine of 56 degrees. And that's going to be, let's see, 26.5 times the cosine of 56. And that's 14.8. Okay. And now for C, now I should point out, these are vectors, right? So the direction matters. So because this bx is going to the left, right, there's actually a negative there. That's important. So here I kind of have to put the negative in manually, right? Kind of realize that bx is going to the left. Now what you could have done, if you don't want to have to do this manually, is you could have said, okay, bx is really at this angle here. Let me do this in a different color. It's going to get a little messy, so I apologize. I'll erase it when I'm done. That this is the angle that bx is at, right? So that angle would be 90 plus 34. So this would be 124 degrees, right? And if you take the cosine of 124 degrees, well, you'll get a negative number, right? So if you were to do 26.5 times the cosine of 124 degrees, you'll get the same thing. It'll be minus 14.8 naturally. So so just, basically if you were to treat this as 124 degrees, that negative would be there naturally. And if you treated this as 124 degrees, it would be positive. So everything would work out. So it's up to you whether or not you want to do the angle measurement that way or just do the right triangle. I think doing the right triangle this way is a little easier, and then just sort of manually putting the negative in at the end. So that's how I'm going to do it, but you don't have to do it that way. And then finally, if we take a look at C, well, C only has a y component, right? There's no x component there, and it's a negative y component. So we could just say that Cy is, negative 31, right? And there's no x component at all, right? So Cx is 0. So those are our components. So now we can get the resultant, right? So if we're going to do A plus B plus C, right? So we're doing this final vector, right? So let's do the resultant. So vector A, right, the arrow means vector, plus vector B, plus vector C. What this really means is you do what's called component-wise addition. So it's AX plus BX plus CX plus, and then here, these are separate, they won't combine, AY plus BY plus CY. And so here, well, what do we have, right? We have 38.8. BX is, so it's a negative, right? So it's going to be minus 14.8. And there is no CX, so plus 0. And then here, we're going to have, now sometimes what they'll do, and I like doing this because my physics background, is you'll put what's called a unit vector here. So this is like all in the x direction. You don't have to do this. This is called the hat notation, but I kind of like it. Plus, and then here you have AY is 20.7, BY is 22.0, and CY is minus 31.0, right? So this is basic, and this would be, say, in the y hat direction, right? In the y direction. So, so what is this going to be? This is going to be 53.6 here. Sorry, that's wrong. I should learn how to do that a little better. That's 24, sorry. 24 even in the x direction, right? And then here, this is going to be, I'll just do this. I mean, I can do it in my head, but I don't want to make any mistakes. So 20.7 plus 22 minus 31, and we get 11.7. So this is plus 11.7 y hat. So that's one way of writing it in the hat notation, right? That would be component notation. You could also write it this way. Sometimes they write it just as an ordered pair, like 24 comma 11.7. We could actually even call this a new vector, like D, and say that this is what D is equal to. Sometimes you'll even see it written like this, is basically the angle brackets just let you know that it's a vector and not just this is really more for like a point, right, x, y, but this is like for a vector. So these are different ways of writing it. You could write it this way, or you could, I think this is probably the best way of writing it, or something like this. But anyway, that's the x component and that's the y component. Now part B asks you to go ahead and write it as a magnitude and an angle with the x-axis. So let's do this here for part B, right? So here, what I'm going to do is, oops, that is not yours. There we go. For part B, let's put our axis here, coordinate axis, like this. And basically, right, we have a point, it's 24 comma 11.7, so this is the x-axis. So like 24, 11.7, I don't know, maybe that would be like right there, right? So that would be 24 comma 11.7, and you draw your straight line there. All right, this is our new vector d. This is the resultant vector. And this is our angle with the x-axis, right? So I'll call that theta is our angle. And basically, right, we have, we have components, right? There's the base of this triangle. This right triangle is 24 units, and the height of the triangle is 11.7 units. And now it's just right triangle stuff. So the magnitude, right, what we would do here, and magnitude is usually written with an absolute value sign because you're basically just like the length of this vector. That's going to be the square root, right, the Pythagorean sum. So it's going to be 24 squared plus 11.7 squared. So that magnitude, right, of that resultant vector, let's see, I'm going to plug that in my calculator. So square root of 24 squared plus 11.7 squared. We get a grand total of 26.7. That's the magnitude. And for the angle, it's going to be the inverse tangent, because the tangent of theta is 11.7 over 24. So the angle is going to be the inverse tangent of 11.7, right, opposite over adjacent, over 24. And if we do that, so the inverse tangent, sometimes it's called the arctangent, means the same thing. So 11.7 divided by 24, and we get about 26 degrees there. So that would be the answer. So this is the magnitude, and this is the angle. So this thing here and this thing here, these are totally equal ways of writing the same thing. So let's move on to an actual physics problem. I mean, that is physics. Vectors are important for physics, but it's not directly physics. This definitely is. So we have a ball that's thrown horizontally from a roof, and it lands 9.5 meters from the base. They want to know what was the initial speed. So let's put this thing together. It's thrown horizontally, right? So I'm going to just play with my colors here a little bit, make this like that. So here's our building. And let me do this is the base of the building here. This is like that. Make that black as well. Be consistent. A little thicker. Okay. So this is the picture, and the ball, right? It's thrown horizontally. So let me sort of draw this thing out. We have a ball. It goes like this. And it's given some, whatever, that's the ball. This is 7.5 meters. That's not really the full distance. Let me do that a little better. Okay. That's 7.5 meters. And this ball, right, is given an initial horizontal velocity. So it has a velocity like this, right? And what's going to happen is the ball is going to do this, right? It's going to basically trace out like kind of half a portion of a parabola. Kind of come down like that. And this is the important thing, right? This is projectile motion, and the horizontal velocity never changes, right? So if I'll call this Vx, I guess, these lengths should be all the same. I'll call that Vx, Vx. Because there's no acceleration. We're ignoring air resistance, obviously. But there's no acceleration in the x direction. Therefore, the speed will never speed up. The x velocity will never speed up or slow, never increase or decrease. However, there is gravity accelerating it down. So this thing, although it starts out with no y velocity, right, it's going to pick up some y velocity as time goes on, right? So here it has a little more y velocity, v, y, and then here it has a lot of y velocity, let's say, because it's being accelerated down. Okay, and we know that delta x, right, we'll call this delta x down here, this is going to be 9.5, so that's how far it travels in the x direction before it hits the ground. And they want to know what was the initial speed. So we want this, basically, right? We're looking for this quantity right here. That's sort of the idea. Now, so basically, right, we want Vx, right? So basically, probably the only one that would work for us, well, let me back up for a sec. The best thing to do here is to write out your knowns and your unknowns, right? But now we have two. We have x knowns, and then we have y knowns. The question is, what do we know? We know a decent amount, actually. What are our x knowns, right? So we can pick a coordinate system, sort of impose our own coordinate system. And I think let's make this the origin. So we'll call that 0, 0. 0 meters x, 0 meters y. If we do that up here, right, well, I don't want to do another dot, but that point up there is going to be 0, 7.5, because it's 0 on the x-axis, but 7.5 height, so 7.5 on the y-axis. So what do we know in the x direction? Well, we know x initial, right? That's 0 meters. We know x final, that's 9.5 meters. We know v initial x, well, we don't know that, that's what we're looking for, sorry. But we know the acceleration in the x direction, that's 0. That's true, always true for projectile motion, is that the horizontal acceleration will be 0. Because it's in the x direction, this object, this ball, is just coasting on its own inertia. There's no force, there's no acceleration in the x direction. For the y, what do we know in the y direction? Well, we know that our initial velocity in the y direction is 0, because they tell you that it's launched horizontally. So whenever they say something is thrown with horizontal velocity, that means it has no y velocity. But obviously it's going to pick up y velocity, so v final y, that is not 0. We know that y initial is 7.5 meters, and we end at the ground, so y final is 0 meters. And we know g, right? G is negative 9.8 meters per second squared. It's the acceleration due to gravity. So the plan of attack here is we're going to use the y information to get the time, and then once we have the time, we're going to use that to get the x information. That's typically how these work, not always, but usually vertical motion is better to solve for time with. Okay, so let's do that. So step one, let's find t using the y motion. What we're going to do is we're going to use this. We're going to say y final equals y initial, so that first kinematic equation, v initial y times t plus a half gt squared. And basically, right, since we have no initial y velocity, this is 0, and since we end at the ground, that's 0. So what we end up with is this equation here. 0 is y initial plus a half gt squared. And you can solve for t. So t, if you go ahead and do the algebra, is going to be 2 times y initial divided by g. Sorry, negative 2. With the negative out. Okay, so then we'll just plug in the numbers now. So the time is the square root of minus 2 times 7.5 meters divided by negative 9.8 meters per second squared. And so when we do that, I'll put that in my calculator right now. So the square root of basically 15 over 9.8, because the negatives will cancel out, get 1.24 seconds. Like that. And then now we can look basically use the t in the x kinematics. So we're going to take that and we're going to look at the x motion. What does the x motion say? Well, we can use basically the same equation, right? X final, just with x variables, is equal to x initial plus v initial x t plus a half that. But again, right, basically that is 0 because there's no acceleration, and we start at x equals 0, so that's 0. And so what we have is this equation, x final is this. This is a vector as well. And so I can go ahead and solve for this thing here, right? So v initial x is x final divided by the time. And so x final, that's 9.5 meters, and the time is 1.24 seconds. And so let's go ahead and plug those in. So 9.5 divided by 1.24, and we get a grand total of 7.7 meters per second. And that's the velocity in the x direction for that one. So let's do one more of these here. This is a good one. So here there's a fire hose. It's held near the ground, so you kind of have this trajectory. If you've ever played Angry Birds, right, that's sort of like the classic projectile motion problem. And it's launched with an initial speed of 6.5 meters. They say speed, so that's a scalar, right? That's a scalar. We don't have to break it up into its components. And the water lands 2.5 meters away. And they want basically to figure out what's theta. So for here, basically, whenever I'll just sort of point this out here. We have symmetry here, right? There is symmetry. In physics, we like symmetry. because it allows us to use, oh, I'm sorry, I dropped my calculator. It allows us to make approximations, and it just generally makes life easier. And it turns out when you have symmetry, basically when you land at the same height from which you launch, you can use something called the range equation. And the range is basically just delta x, or we know what delta x is here. It's 2.5 meters. And what the range equation says, sometimes they'll call it r, but I like to call it delta x, because that's really what it is. It's this. It's v initial squared sine 2 theta over g. Again, you can only use this when you land at the same height from which you launched. But in this case, that's the deal. They want theta, right? So we basically have numbers here, right? We can basically go ahead and rearrange this stuff, right? So if I can kind of solve for sine 2 theta, if I do the algebra, what I'm going to get is that this is delta x g over v initial squared, and then take the inverse sine of both sides. So you get 2 theta is the inverse sine of delta x times g over v initial squared, and then divide both sides by 2. And so you get your grand total is theta. It's going to be this whole thing, right? So the inverse sine of, delta x, I'll call it g delta x, the order doesn't matter, all divided by 2. So let's go, close that out. So let's go ahead and plug these numbers in. So that's going to be the inverse sine of, okay, so we have negative 9.8 for g, and then we have here delta x, which is, what did I say it was? 2.5 meters? Yes, 2.5 meters. And then divided by, oh, actually g here is positive. There's a reason for that. We'll talk about it. It's basically because the negative is kind of absorbed in this. Well, it's kind of complicated. But anyway, it's not that complicated. It's just a trig identity thing. But when you use this equation, make sure you treat g as positive. That's an important point. The initial velocity is 6.5. So let's put that in there. 6.5 meters per second squared. Close this thing up, and then divide this whole thing by 2. So I'm going to put that in the calculator real quick. So we get, so the inverse sine, oops, let's say the actual sine. Inverse sine of 9.8 times 2.5 divided by 6.5 squared. I'll do that part, oops, just bear with me. Do that part first, close up that parentheses. Get 35.4, let's say, divided by 2. So this is 35.4 degrees divided by 2. So it's going to be 17.7. So theta, right, theta naught, whatever they want to call it, 17.7 degrees. Okay. But that's not the only angle that'll do it, right? Basically, you can add, because you go back, if you think back to the unit circle, right? Let's see. So let me draw this out. Well, okay. If you remember your units, you have the quadrants, right? And the way we learned it was like all students take calculus, right? So all, I don't know, you might have learned it some other way. Students take calculus. And basically this gives you, in this quadrant, quadrant 1, all of the trig functions are positive. In quadrant 2, they're all positive. In quadrant 3, they're all positive. Quadrant 4. But the bottom line is that there is more than one angle. You get more than one solution when you solve this thing here. So let me sort of explain what I'm getting at here. So we have, if we go back to that solution, right, where we got to this part, where basically we were like, the theta, well, we did the sine theta here. If you were to solve this thing, right, you would get 35.4 degrees, but it's not just 35.4 degrees, because we could do it this way, right? We have, this is 35.4 degrees, and this one works, but then also this one would also give you a positive sine, 35.4 degrees. So what you would have to do to get this angle, so this is one angle here, and then the second angle would be this one. Right, that would also work. And so how do you do this? Well, basically this is going to be 90, and then whatever the difference here is, right? So 90 minus 35.4. So if we do 90 minus 35.4. That's 54.6 degrees. So this angle here is going to be 54.6 degrees, which is this piece here, plus 90, right? So that's going to be 144.6 degrees, right? But then we divide that by 2 over here, right? So we divide that by 2. So that's going to be, so 144.6 divided by 2. So that'll be 72.3 degrees. So really, like, again, there are two solutions. It's going to be this, and it's also going to be comma 144.6 degrees divided by 2. So we'll get another solution here, which is 72.3 degrees. So these are the two solutions that work. And then if you were to, basically they'll give you the same, you'll get the trajectory, right? So just sort of briefly, if we were to just sort of roughly sketch this thing here, I guess I'll do it this way. Like this. You know, you would have basically one trajectory would look maybe like this. Let's do it like this, right? And then one trajectory would look, you know, maybe something like this. Yeah, like that. Okay. So like this angle here, like the red angle, right? That would be. Oh, sorry, that's terrible. So the red angle, right? That, or the red trajectory would correspond to the bigger angle, so 72.3 degrees. And the blue angle, the blue trajectory, that would correspond to the 17.7 degrees. So those would be the two different angles. They give you the same range. Okay, I have one more here that I want to do. They say a ball is shot from the top of the building with an initial velocity of that at this angle above the horizontal. They want the vertical, they want the components of the velocity, and they want to know, we have another building the same height, that's 55 meters away. How far below the top of the building will the ball strike the nearby building? So let me sketch this thing out. So here, I'm going to make this the ground here. Yeah. That'll be the ground. And then we have these two buildings. And they're the same. The buildings are the same height, right? So do it like that. Put this one over here. I'll make that the same color, black. Same. I'll just copy that and put a new one here. Put this thing here. Okay, cool. Okay, so the ball is shot like this. Sort of up like that, I guess. Well, it's 42 degrees. Yeah, I think that looks sort of reasonable. Okay, so the ball it does that sort of thing. And we don't know exactly what it's going to do, but they're sort of giving you a hint here, and they're saying, well, it's going to maybe, you know, do something like this, maybe. Right? That's sort of the assumption, is they want to know how far below it hits, right? So we're basically looking for, like, I don't know if we want to call that like H. That's what we're looking for. Okay, and so we know delta x is 55 meters, right? So delta x is 55 meters. Okay, cool. And this, okay, so here we have to break this thing into components, right? So this is 18 meters per second, call that V0, right? And then, so this piece here is going to be V0x, and this piece up like this is going to be V0y. And this angle is 42 degrees. So we're going to do SOHCAHTOA, right? So we'll deal the cosine of 42 degrees, right? That's adjacent, which is the VOX over V0. So VOX over V0. And so if we rearrange this, we'll get that the x component, V0x, that's V0 cosine 42. And we can just plug that in because V0 is 18. So that's 18 meters per second. Cosine of 42 degrees. So I'll put that in my calculator. Let's see, 18 times the cosine of 42. 13.4 meters per second. Okay. And then we'll do the same thing for V0y. Basically, it's just going to be the sine by the same logic. So V0y, that's V0 times the sine of 42 degrees. So 18 meters per second times sine 42 degrees. Let's see what we get. So 18 times sine 42, 12.0. Okay, so those are the components. That's V0x, V0y. Okay, so now what do we know? Well, we can actually get the time pretty easily because we know delta x and we know V0x. And if we look at the x motion, right? So let's do that. Let's look at x motion. Now I said before that usually we look at the y motion for time, but in this case it would make more sense to look at the x motion. I'll show you why. Again, there's no one way of doing these things. You just got to kind of play around with them and sort of get used to them. I know that takes some practice, but it's really the only way to do it. So what do we know? Well, we know V0x is 13.4 meters per second. We can say that we start at 0, and we can say that we end at 55 meters. And really importantly, again, because this is projectile motion, we know that the acceleration in the x direction is 0 meters per second, and this is what's going to make our life a lot easier. So we can use this equation, right? X final equals x initial plus V0 xt plus a half axt squared. And so again, like what's 0? Well, actually we don't, yeah, okay, that's perfect. Sorry about that. So this is gone, because that's 0, and this is gone. And so we get this very simple relationship again, right? That the final position is just equal to the speed, or not the speed, the x velocity times time. And so we can solve for the time, right? So the time is x final over the initial x velocity, and we have numbers for both of these. That's 55 meters divided by 13.4 meters per second. And let's see what we get. So 55 divided by 13.4, and we get 4.1 seconds. So that's how long the trip takes. So now what I want to do is I want to find the final y position, right? So we're actually going to take somewhat of a pre-calc based approach here. Not necessarily pre-calc, but basically I can say, look, y final is equal to y initial plus v initial yt plus a half gt squared. And I want y final, right? That's basically what we're looking for. We know that we start at our y initial, we started at 55 meters, right? That's how, sorry, do they say how tall this thing is? I don't know. They just say it's the same height. We don't know the initial position. Let's see, top of the building. We just know that they're 55 meters away. What we could do here is, this actually is probably the best thing, because you can actually pick your 0 point wherever you want. So what I'm going to do is I'm going to basically make this y, I'm going to say, assume that we start at y equals 0, right? You can place your origin wherever you like. And so the beauty of that is we're going to say, I'm just going to define this to be y equals 0. So y initial, I'm going to call that 0 meters. So if we end on the ground, we're at negative y. And that'll make life a lot easier. So this is going to be 0 meters, right? Plus our initial velocity in the y direction, well, we already solved for that back in part A, that's 12 meters per second, times our time, and our time is 4.1 seconds, plus a half negative 9.8 meters per second squared, times the time of 4.1 seconds squared. And so we'll get our y final here. So bear with me. So 12 times 4.1 plus, plus a half. So a half of 9.8 is 4.9 times 4.1 squared. And we get negative 33 in the end, right? We get negative 33.17. So negative 33.2 meters. So that's how far below, right? We're basically 33.2 meters below the top of the building. Because the top of the building is defined to be y equals 0, so if it's negative 33.2, that's how far below you are. So that's basically the idea. So I hope you found this stuff pretty useful. It's a couple four problems, so they cover a lot of the stuff that you'll see in the chapter. So, as usual, any questions, let me know, and I hope you find this informative.